Have you ever watched a gymnast pull off some incredible flip, or just stared at a skyscraper and wondered, how in the world does that stay up? Well, the answer to both lies in a single, totally invisible point that actually governs how everything moves and balances. Today, we are diving deep into that fundamental concept, the center of mass. So, to get started, let's just chew on this question for a second. How can something that weighs over a ton, like a car, balance perfectly on a point so small it honestly looks like some kind of magic trick? And, well, here it is. This is a real picture. There are no strings attached, no camera tricks. It's just a fantastic, real-world example of a core physics principle. And believe me, by the end of this, you're going to understand exactly how it works. Okay, so to crack the code of the balancing car, we've got to find its balancing point. And our journey to find it actually starts by taking a much closer look at something we think we already know: gravity. We casually say gravity pulls the car down, but that's a huge simplification. The reality is gravity is pulling down on every single atom, every molecule, every little nut and bolt that makes up that entire car. We're talking about an almost infinite number of tiny forces all pulling at once. So, in the real world, an object is getting hit with this incredibly messy swarm of gravitational forces. Trying to calculate anything with that would be an absolute nightmare. So physicists came up with this brilliant, elegant shortcut. What if we could just pretend all those forces were one single force, acting on one single point? This amazing simplification, this one special balancing point, it has a proper name, of course. And this is it. The center of mass. It's this unique spot in any object where, for all intents and purposes, you can imagine all of its mass is concentrated. If you can support just that one point, you can support the entire thing. That is the secret to the balancing car. So where do you find this magical point? Well, for something simple and symmetrical, like a plain wooden ruler, where the mass is spread out evenly, that's a uniform body, it's easy. It's right in the geometric middle. But for a non-uniform body, like a car with a super heavy engine in the front, it gets a little more interesting. The center of mass is going to be pulled toward the heavier parts. So for something complicated like that car, or maybe even a bunch of people, how do we find that exact balancing point? Well, it turns out we can actually calculate it. The absolute best way to think about this is a seesaw. If two people with different weights want to balance, the heavier person has to sit closer to the middle, right? Well, that pivot point, the fulcrum, is the center of mass for that two-person system. What we're actually doing with that seesaw, in mathematical terms, is finding the weighted average of their positions. Each person's position is weighted by how much they weigh. Heavier people have more pull, more influence, and they drag that balancing point closer to them. All right, let's give it a shot. Picture 3 people, all different weights, and they're standing on a long beam. Where would you have to put the pivot point, the fulcrum, to get all 3 of them to balance perfectly? Okay, let's get our variables straight. At position 0, we've got a 70-kilogram person. Then 4 meters down the line, there's a 60-kilogram person. And finally, 10 meters from the start, we have our heaviest person, coming in at 82 kilograms. So here's how we solve it. It's actually pretty simple. First, you take each person's mass and you multiply it by their distance from the start. So that's 70 times 0, 60 times 4, and 82 times 10. You add all those numbers up. Then you divide that total by the total mass of everybody, which is 212 kilograms. And what do you get? The balancing point for this whole system is exactly 5 meters from the person on the far left. Okay, now we get to what is probably the most profound, almost unbelievable thing about the center of mass. It has this kind of special inertia that's really unlike anything else. Think about a firework exploding in the sky. It flies up in this beautiful, smooth arc, and then, boom, it bursts into 1,000 little pieces. But what happens to the center of mass of that big cloud of fragments? Well, this quote right here gives us the clue. The explosion is all internal forces. And here is the absolutely amazing part. Even as all those little pieces are flying off in every direction, the average position of all that mass, the center of mass, it just keeps on going. It follows that same perfect, smooth arc as if the explosion never even happened. Internal forces just cannot change the path of a system center of mass. Only an external force, like the wind, can do that. You can see this exact same thing happen on a lake. Let's say a person is in a canoe. As they walk toward the front of the canoe itself actually slides backward in the water.
Why? Because the person and the canoe are a single system. And for that system center of mass to stay put, which it has to since there are no external pushes or pulls, as the person's mass moves forward, the canoe's mass has to move backward to compensate.
So, what's the big takeaway from all this? Well, this one single point helps us simplify the motion of everything from exploding fireworks to spinning galaxies, and it tells us something really fundamental. A system can't move itself. To change where its center of mass is going, it has to push against something outside of itself.
And that leaves us with one final, and I think fascinating question. If you and the Earth are a system, and your own muscles are just an internal force, how does pushing with your legs actually get you anywhere? What is the external force that lets you move your center of mass forward when you take a step? Think about that for a minute. That's physics at its most personal.